This video is on the objective determine the critical value or values of a one-mean z-test at a given significance level to define a rejection region. All right, so this is one step in performing a hypothesis test with the critical value approach. Now remember, there are two approaches to a hypothesis test. You could take a critical value approach where you find a critical value or critical values depending on the significance level, and then you set up your rejection region. And then there's the p-value method where you find the p-value for your particular test statistic. Right, this is for the critical value method, a critical value approach. And this is number one. This is the first video on this, so I'll take a little more time to explain things as we go along. Right, so let's take a look at the problem in your Newton Alta homework. So again, if you're unfamiliar with the topic, want to see more about it, click on more instruction, look at their videos, their examples, their notes, and hopefully that helps you. Alright, so here we're asked to determine the critical value or values for a one mean z-test. So remember, if we're using z, that means that the population standard deviation is known, right? Sigma is known. But that doesn't bother us here. It's not going to affect us here. We're just asked to find critical values at the 20% significance level if the hypothesis test is left-tailed, right? Meaning that, if I were drawing it on paper here, if I say I have a let me get rid of the calculator. If I have a left-tailed test, remember there's some claim that's made. I don't know what that is. They didn't give us any information. This isn't like a full-fledged problem. Then from the claim you have your hypotheses, the null hypothesis and the alternate hypothesis or alternative hypothesis. The null hypothesis, we're going to be assuming that mu equals something, right? Some mu sub 0. That we're going to assume that the population mean is equal to some value. And then here, they told us we have a left-tailed test. That means our alternative hypothesis looks like this. It's going to be, we're going to have the alternative hypothesis will be that mu, the population mean, is less than this, whatever this mu sub 0 is, this value. So again, it's left-tailed. And then what we would do is we take our sample and it would have a certain size, right? And a certain sample mean, right? And then we apply the central limit theorem. Remember, by the central limit theorem, if sigma is some known value, right? If sigma, the population standard deviation, is a known value, by the central limit theorem, the distribution of sample means for samples of size n would be approximately normal, with a mean of mu x bar and a standard deviation of sigma sub x bar, where the mean of these means, the mean of the sample means for samples of size n, is the mean of the population, and this is coming from the null hypothesis, right? This is what we're assuming to be true, right? And the standard deviation of these x bars is the standard deviation of the population, which is known, divided by the square root of the sample size. And then I would draw a picture, right? I'll draw a picture, some normal distribution. So we have the x bars here, and normally distributed. So I got some symmetrical bell shape, and underneath the peak is the value of mu sub 0, the value of the assumed mean of the population. And the standard deviation of this distribution is whatever sigma is divided by the square root of n. All right. Now, to set up, to find these critical values they're talking about, we normalize this distribution. Remember, this means change everything to z-scores. Now remember, z-scores, you take, whatever mean value you get, you take your value, you subtract the mean value, and divide by the standard deviation. Right? Z-score is how many standard deviations away from the mean are you. So I changed this to a standard normal distribution, right? Remember Z has a mean of 0 and a standard deviation of 1. I changed this to the standard normal, where remember the z-score of the middle is 0. Right? And then we take a look at our sample mean. Right? When I took a sample and got its mean, we'd mark that off somewhere. There's our sample mean, and then we change it to its z-score, z sub x bar or whatever, and that would be the test statistic. Sorry, I'll call it z-test. We'd change our sample mean into its z-score to get a test statistic. Now, it's here where we're finding our critical value or critical values. Now, since it's a left-tailed test, it was mentioned to us that it's a left-tailed test. And the significance level, that alpha is 20%, 0.20. They told us it was 0.20. So what I'm looking for is what value has 20% of the area below it, to the left of it. And that would be the opposite of whatever z sub 0.20 is. Remember, z with a subscript of 0.20, this is the z-score with 20% above it. Right, this is the z-score with 20% above. Hopefully you remember this. Z's with subscripts meant that the z-score with that area above. Well, then I want the opposite of that, right? Because I want what z-score has an area of 20% below if it's a left-tailed test. And then this region where the area is 20%, right, area equals 0.2. This is our rejection region. All right, this would be our rejection region. And then if our test statistic fell in that region, we would reject the null hypothesis. And if the test statistic doesn't fall in that region, then we don't reject the null hypothesis and accept it. Right. So we're looking for this value here. Right. And they gave us a chart. Right. They gave us some special, special z values. Right. This is the z-score with 80% above it, so negative 0.42. This is the z-score with 40% above it. This is the one we want. Right? I want the z-score with 20% above it, 0.842. So then this value, let me pull up my paper again. So then this value, though, is negative 0.842. Okay, because they told us the z-score with 20% above it is positive 0.842. So take the opposite of that. That means the z-score with 20% below it, right, using the symmetry of a normal distribution, is negative 0.842. Right, so that's what I'm entering. I'm going to click on that, negative 0.842 for the critical value of this test, right? The entrance to the rejection region. Now, if it were a right-tailed test, then I would just use this value, right? A right-tailed test critical values are the z-score with that percentage above it. And then for two-tailed tests, the critical values are, there are two critical values, one with half of alpha above it and one with half of alpha below it. And in fact, let me refresh your memory there. I got this written out from an earlier video. When you have a left-tailed, right-tailed, or two-tailed test, let's get rid of this stuff. So, here's a left-tailed test we just saw. Remember, the critical value for a left-tailed test has area of alpha right, the significance level to the left. And then, again, if your test statistic falls in that area, you reject the null hypothesis. If it doesn't, you don't reject. Then for a right-tailed test, you just kind of flip that. Right? For a right-tailed test, the critical value has an area of alpha to the right. And again, if your test statistic falls in that region, you reject the null. If it doesn't, you don't reject the null hypothesis. And then for a two-tailed test, you kind of cut the rejection region into two equal halves. You're going to have two critical values. There are two critical values, one with an area of half of alpha to the right, this critical value 1 I called, and then the other one with the area of half of alpha to the left. That way the total area of the rejection regions is alpha. All right. So you got two of them for a two-tailed test. Okay. So hopefully that refreshes your memory. I brought that up before in a previous video. Hopefully you've been watching. And yeah, and of course, read your answer explanations when you're right or wrong. Read them when you're correct to make sure that your reasoning was right and you didn't just luck out. And of course, read it when you're wrong to see if you can find where you went wrong, and then hopefully next time you see a problem like this, you'll do better. Okay, and I don't think there's a second part to this. There is not. So hopefully that video helps you when you're going. Now I'll put out another one. This was just number 1. Hopefully this video helps you when you're going over that kind of a problem on your own. And thank you very much for watching.